Welcome to ATMOS 5000, day number 36. We're covering Chapter 10 of the Stull textbook, sections 10.8 and 10.9. Specifically, we'll be introducing the continuity equation. We'll be talking about the divergence and convergence equation and how divergence and convergence can lead to upward motion in the atmosphere. We'll also talk about boundary layer pumping. We'll introduce the concept of vorticity, which is the rotation of a fluid, and then we'll also introduce deformation. So here we have the continuity equation, which is essentially an expression describing how the density of an air parcel changes over time. There are two terms in the continuity equation. The first one is the advection of density differences, and the second term is due to the expansion or compression of the air itself. And if you assume that the air parcel is incompressible, so that would be like liquid water as opposed to the atmosphere, then you can assume that there is no expansion or compression, and that term delta U over delta X plus delta V over delta Y plus delta W over delta Z is going to be equal to 0. And then from an Eulerian sense, the change in the density would then be only due to the density advection. So here we have a mathematical expression for the horizontal divergence and convergence. It's defined as delta U over delta X plus delta V over delta Y. And there are two types of divergence or convergence. One is directional divergence, and the second is speed divergence. And in directional divergence, you essentially have air parcels that are moving away from each other. Directional convergence, air parcels are moving towards each other. And for speed divergence, you have air parcels that are accelerating away from other air parcels. And for convergence, you have deceleration and the piling up of air parcels. So here we have an example of air that is flowing around a high pressure and then around a low pressure and then around a high pressure. And if we deal with the gradient wind balance, you'll remember that air flowing around a high will be supergeostrophic. It will be flowing parallel to the isobars, but will be stronger than the geostrophic wind. Then as it transitions from moving around the high to around the low, it's going to be geostrophic balance because there's no curvature. And then as you curve around the trough, the wind will become subgeostrophic as the Coriolis force and the centrifugal force are balancing the pressure gradient force. And then it becomes geostrophic as you move around the low again, where the isobars are straight, and then becomes supergeostrophic once again. The acceleration and deceleration of the airflow will lead to regions of convergence and divergence. So for example, as you move around the high, you're moving from supergeostrophic to geostrophic wind, so the wind is slowing down. And as it slows down, it piles up, and that's a region of convergence. And then, of course, as you are accelerating from subgeostrophic to geostrophic winds, and then accelerating towards supergeostrophic winds, you have an area of divergence where the air parcels are actually moving away from each other. And this is an example of speed divergence aloft, but you can also have directional divergence as well if the isobars or the lines of constant geopotential height are not the same distance apart all the time as well. Boundary layer pumping is a mathematical representation of what happens when you have convergence at the Earth's surface. So if you have converging air in the horizontal, it's not able to essentially move through the ground. So as you compress it, it's going to respond by moving in the vertical direction. So here we have a cylinder that has a volumetric motion in towards the center of this cylinder, and the cylinder has a radius r and a depth delta z. And so we can define the vertical motion outside of this cylinder upwards as 2 times the volume of the inflow times delta z, which is the height of the boundary layer, divided by r, which is the radius of curvature of the motion. So we often think of this as an idealized cylindrical extratropical cyclone, so a big low pressure zone where friction is causing the air to cross the isobars from high to low. That leads to a volumetric motion in towards the low, which will result in an upward vertical motion due to the surface convergence. Vorticity is a term that we use to describe the rotation of a fluid, and you can have vorticity, rotation of a fluid around the I direction, which is the X direction. You can have rotation around the Y direction, which is the J hat, or you can have rotation around the K axis, which is the Z direction, or the vertical axis. So here we're looking down on this motion, this XY plane. So using the right-hand rule, if we basically take our fingers from our right hand and curl it in the direction of the motion, our thumb will be pointing up. And that is how we define the direction of the vorticity. So in this case, this horizontal rotation of the fluid using the right-hand rule will be defined as relative vorticity in the k-hat direction or the z direction. And this relative vorticity mathematically is delta v over delta x minus delta u over delta y. Now in this class we're not going to be defining the vorticity in the horizontal around the x or around the y, but mathematically they're very similar, and we'll reserve that for a later class. But just now we have an example of a way to calculate the magnitude of the rotation of a fluid using the concept of vorticity. We also have deformation, and there are two types of deformation. There is stretching deformation and there's shear deformation, and you can see that they are mathematically different from the divergence and convergence and different for vorticity. And the total deformation, F, is just equal to the square root of the squares of the stretching deformation and the shear deformation. So let's take a look at what these actually are. So on the left, we have an example of stretching deformation. And so the green arrows essentially are showing the airflow. The light green box was the shape of the original air parcel. And then over time, the directional flow is such that it will tend to elongate and stretch the original air parcel in the horizontal along the x-axis in this case, and shrink it along the y-axis. So you can imagine if you had cold air to the north and warm air to the south, wind that was flowing in this direction would cause a deformation, which would cause a tightening of the isotherms, which would actually develop into a frontal boundary. If you want to think of it that way, this is the one of the ways that you can actually develop frontal boundaries as through stretching deformation. Shearing deformation is the same sort of thing, except that it's tilted at an angle away from that. So we have a initial air parcel that was a square, and the shape of the wind shear in this case is such that it deforms the shape of the box into a triangle, if you want to think of it that way. And it is once again bringing air parcels closer together in this axis that is the axis of contraction, and then it is expanding or stretching essentially through the shearing process along the axis of dilation. And both the stretching deformation and the shearing deformation are both essential components of frontogenesis, which is the generation of fronts in the Earth's atmosphere.